This video is part 2 of a lecture from section 5.4 of Math 311, a course on linear algebra at Western Illinois University. In the last video, we did this example. We showed that when we diagonalized this symmetric matrix, this real symmetric matrix, it was business as usual, except that in addition to getting these two eigenvectors that were linearly independent, they were actually orthogonal. And that we could, once we have an orthogonal set, we can normalize the vectors and get an orthonormal set, and then get an orthogonal matrix, and then take that use that orthogonal matrix to diagonalize A. And we said that if A was a matrix like this, then we said it was orthogonally diagonalizable. That is, if there was some orthogonal matrix Q, such that Q transpose AQ is equal to some diagonal matrix D. And we also showed last time that any orthogonally diagonal matrix is symmetric. Our next job is to show that any real symmetric matrix is orthogonally diagonalizable. And we need to prove a couple results here. Now, I should say this is going to be this is very theoretical, okay? You won't be required to reproduce these proofs. And if you don't quite understand every single detail, that's fine. But I do want you to see how everything seems to follow from this. I mean, you certainly don't need to know these. You do need to know these results, if not the proofs. Okay, the one we're going to prove now is number 2. That if A is real and symmetric, then the eigenvalues of A are real. Now, again, we've sort of said that there are some matrices that don't have any real eigenvalues. Okay, that they're complex because we know that the characteristic polynomial, as a polynomial, has to have some roots, but sometimes they're all complex and not real. But we're going to prove that if A is real and symmetric, then all the eigenvalues of A have to be real. Okay, so the way we do that is as follows. So why is this true? Okay. Let lambda be an eigenvalue of A, and let's say with eigenvector V. Right now, so I don't want to. Normally I would write a little vector hat there to denote that this is a vector, but in this particular case, I'm not going to do that because I'm going to let a little dash or above V to represent something else. This means AV is equal to lambda V. Now, V, the components of V could be real, but they could also be complex, not real. So I'm going to write V as in this form: A1 plus B1I AN plus BNI, where I, of course, is the square root of -1. And every complex number, of course, is going to be in this form. We're also going to, let alpha be A plus, in the form of A plus BI. We're going to eventually show that this B has to be 0, but let's assume it's not, and we'll just write it this way. Then if we take we have this thing where we take the conjugate of A plus BI. In this case, that would be lambda. We put a bar over that. That means we're taking the conjugate, and what that means is we're just changing the sign of B as A minus BI. So we're going to define another vector V bar, where we're taking the conjugate of all the components of V. So this would be A1 minus B1I, AN minus BNI. Okay. All right. Now, then it's not very hard to see that now A is real, so if we were to take, we can basically take the conjugate of both sides of this, and what we would get is that A V bar is equal to lambda bar V bar. So basically the conjugate of lambda is also going to be an eigenvalue of A, where the eigenvector is V bar. Okay. This again, this only works if A is real. Okay, because if A is real, then all the entries of A are going to be unchanged by this conjugation thing. So that's why we have that. All right. Well, then we can take the transpose of both sides. And this will be V bar transpose A transpose. And this is now lambda. Oops, sorry, you can't see that, can you? My bad. V bar transpose A transpose is equal to lambda. We can just, lambda bar is just a scalar. It's a complex number. So we can just basically pull that out, and this will be V transpose. And then we're also going to use the fact that A is symmetric, assuming A is symmetric, so this is just, so V bar transpose times A is equal to lambda bar V transpose. Okay. All right, now, to show that lambda is real, we're going to show that lambda has to equal lambda bar. And we're going to do just a couple ways, but one thing we have to note is that V bar transpose times V, this is really the same thing as the dot product of V, or V bar and V. That is, we're taking the dot product of these two, this vector and this vector. And if we do that, remember we can, we use the fact that, x plus yi times x minus yi is going to be x squared plus y squared, because I, after all, is the square root of -1, and x squared minus negative y squared is just plus y squared. So this is going to be, this times this will be a1 squared plus b1 squared. The next component will be a2 squared plus b2 squared. Then we have an squared plus bn squared. Okay. And you can see because the a's and b's are real, this has to be non-negative. There's no way this can be negative. And in fact, this is going to be positive. And why can't it be zero? The only way this can be zero is if all the a's and b's are zero. And if all the a's and b's are zero, then all the components here are zero, which means that v is zero, the zero vector, and the zero vector can't be an eigenvector. Okay, so this is strictly positive. Now, if we take lambda times v bar transpose v, we can pull the lambda inside because it's just a scalar. And you can group the lambda v together. And of course, lambda v is AV. And now we also know, of course, that that A is symmetric, so this is the same thing as A transpose. And then this is going to be the transpose of a V bar. And a V bar is going to be lambda bar, V bar, transpose V. Well, this is just lambda bar times V bar transpose V. And now we see that lambda times this number is equal to lambda bar times this number. And this number is strictly positive, and this is strictly positive. So the only way that this can be equal, so there's no way this can be zero, so the only way this can happen is if lambda equals lambda bar, and that means that lambda is real. All right, you have, this is if you think about this, we're just sort of using the properties of the transpose and the associativity of matrices and the properties of the transpose, and using the fact that A is symmetric, but everything follows. You just have to keep track of what's a vector and what's a scalar here, but this works. So this shows that all the eigenvalues are real. The next result we need to show is that that's why we want to explain why we get orthogonal eigenvectors when we have a symmetric matrix and if the corresponding eigenvalues are different. Okay, so why would that be? So we're trying to show that if A is a symmetric matrix, then any two eigenvalues corresponding to any two eigenvectors corresponding to distinct eigenvalues are orthogonal. Okay, all right. This is going to be hopefully a little easier because now we're not going to deal with complex numbers. We don't need to anymore because we know everything's real when we have a real symmetric matrix. So let's suppose. So why is this true? Okay. So suppose that we have AV1 equals lambda 1 V1 and AV2 equals lambda 2 V2. Okay, we're not doing conjugation anymore. These were just going back to our usual vector notation. Okay, so V1 and V2 are eigenvectors corresponding to lambda 2 and lambda 1. And lambda 1 is not equal to lambda 2. Okay, all right. Now we just play around with some equations. Let's take lambda 1 times V1 dot V2. Okay. This, of course, since lambda 1 is a real number, this is the same as the dot product of lambda 1 times V1 and V2. And because of lambda 1 is an eigenvalue of A, this is A V1 dot V2. But this is the transpose of A V1 and V2. But this is going to be V1 transpose A transpose V2. And we can group of course, A is symmetric, so A transpose is just A. And we can group the AV2 together, and that will be lambda 2 V2 and then because lambda 2 is just a real number, we can pull that outside, and this will be V1 transpose V2, which is just lambda 2 times V1 dot V2. And now what if you can see here is that lambda 1 times this is equal to lambda 2 times this. Okay, these are different, so that the only way that this equation can hold is if V1 dot V2 is 0. Okay, which means that V1 and V2 are orthogonal. Okay. Okay, again, let this sink in. Think about this, but don't think about it too much. All right. Actually, this is probably the easiest of the three things that we're proving in this tape, in this video. Okay. The next result definitely is not the easiest, but it's a very important result. And it's so important that it's a theorem. Okay, it's a spectral theorem, which now we're going to put everything together and see that if A is an n by n real matrix, then A is symmetric if and only if A is orthogonally diagonalizable. Okay, now we already proved that anything, if it's orthogonally diagonalizable, it must be symmetric. Okay, so here's the proof. We from number 1, we know that orthogonally diagonalizable implies symmetric. Okay, so now we're going to suppose that A is symmetric. All right. And then that means we can apply the last two things that we proved. All right. Now what we're going to do is, this is not going to be a real rigorous proof here. We're going to prove this in the case of a 2 by 2 matrix. And then we're going to prove it in the case of a 3 by 3 matrix. And then we're going to hope that you can look at the general proof in the book and see what how all the other cases are kind of similar to the case of a 3 by 3 matrix. Okay, so let's say if A is symmetric, we know that A has a real eigenvalue. Okay. Okay, from number 2, and we'll see that V have an eigenvector. Okay, so AV1 equals lambda V1. Okay, for some eigenvector V1. Now, what we're going to do is we're going to assume that V1 is also a unit vector, that its length is 1, and we can always assume that because we can always replace V1 with V1 divided by its length. Okay, so we can assume that V1 is a unit vector, and we can replace V1 with 1 over its length times V1 if necessary. Alright, so V1 is, in addition to being an eigenvector, it's a unit vector. Alright. Now, we're going to find another vector W, which is not in the span of V1. Okay. So then, if we take V1 and W, then this is a basis of R2. Okay. Right, because these are clear. This shows that V1 and W are not linearly independent, are not linearly dependent. So this is linearly independent. This is a basis of R2 because the dimension of the subspace they generate is 2, and it must be equal to R2. Now we use our Graham-Schmidt process to get another basis, an orthogonal basis. And we're going to we already know that V1 is normal, and we can normalize V2 again by doing this step. So through Graham-Schmidt and also normalization, we get an orthonormal basis. Of R2. Okay. All right, and that's great because now we can let Q be the matrix whose columns are just V1 and V2, and this will be an orthogonal matrix. Okay. And in fact, A times Q is going to be AV1, AV2. And remember, AV1 is still an eigenvector, so this is going to be lambda V1, AV2. And then we can actually write this as a product of this matrix, lambda 0 something something times V1, V2. If you do the actual process here, first column, I mean, you can see, you know, check that the first column, which is, if the first column is lambda v1, then that's why this thing has to be 0. So this right here will be something times v1 times something times v2. This is just going to be lambda times v1 plus 0 times v2. So that's where this comes from. But this is still q, right? And q is still orthogonal. So the inverse is q transpose. So we get q transpose aq is, let me just see here. Actually, I think this we might have to. I'm sorry, we need to move this over here. So, yeah, this is. Sorry, it should be v1, v2, I think, times lambda star 0 star. Okay, sorry about that. And this is q. So now we can multiply on both sides by q transpose, and we get q transpose aq is going to be this matrix lambda star 0 star. But this is easy to check that this is symmetric, like we did before. If we take the transpose of this, we get q transpose a transpose q, and a transpose is a. So this is equal to its own transpose, so this has to be equal to its own transpose. And because this is 0, that means that this has to be 0. Okay. So we get that q transpose aq is equal to lambda 0 0 star. Okay. And we can just take this as d. Right? All right. And that's how that works. Okay, that will then you can say that proves that A is orthogonally diagonalizable. All right. Let's briefly talk about the 3 by 3 case. So let's say that A is a 3 by 3 symmetric matrix. Okay. And again, A has an eigenvalue, so let's say let lambda is an eigenvalue of A, and let's say that A v1 equals lambda v1 for some eigenvector v1, and we're going to assume that the length of v1 is equal to 1. Okay. And then what we can do is we can come up with a basis of R3 where the first vector is v1. We can take v1, take some vector which is not in the span of v1, we'll call it w2, takes another vector which is not in the span of v1 and w2, and that will be w3. Okay, and let's say that that's a basis of R3. And again, through Graham-Schmidt and normalization, we can get an orthonormal basis. v1, v2, and v3 is an orthonormal basis. Of R3, and then we can let Q be a matrix whose columns is v1, v2, and v3. Okay. And then AQ will be AV1, AV2, AV3, and we know that because v1 is an eigenvector, this is lambda v1, av2, and av3. Okay, And I'm just going to double check so we don't get confused again. Or I don't get confused again. Okay. Now, see, this isn't a good thing. We're not. I'm not putting this on a test, right? Okay. Okay. Well. Okay. Well. Once again, I think we can write this as what we did here is we have Q. Okay, so this would be. Do I want to make the same mistake again, or as I write the first time? Okay. So this will be V1, V2, V3, and then we'll have lambda, lambda 0, 0, star, star, and then some matrix B here. Okay, if we do that, where B in this case will be a 2 by 2 matrix. This is Q, so multiply by Q transpose, and now this is equal to lambda 0, 0, star, star, B. Okay, and this is symmetric again. So that means this is symmetric, which means that these have to be zeros, and B is real and symmetric. So B is a real symmetric, and it's 2 by 2. So once again, from the previous case, B is orthogonally diagonalizable. So B can be written as Q1 D Q1 transpose for some 2 by 2 orthogonal matrix Q1. So then this becomes, so Q transpose AQ becomes lambda 0, 0, 0, 0, Q1 D Q1 transpose, where D is 2 by 2 and diagonal. And then this, take my word for it, this can be factored as 3 different matrices. 1, 0, 0, 0, 0, and then Q1. This is lambda, and then D, and then this is 1, 0, 0, 0, 0, Q1 transpose. And then you can see that this will clearly be diagonal if D is diagonal. And if we call this Q2, then this is Q2 transpose, and then you can check that Q2 will be orthogonal. And then we can so Q2 inverse is Q2 transpose. So we get Q2 transpose Q transpose times A times Q Q2 is equal to this matrix. We'll call this big matrix, we'll call it D1 if we want. Okay. And then this is Q2 transpose A Q2 equals D1. And then finally we just use the fact that because Q and Q2 are orthogonal, that means Q2 is orthogonal. And D1 is diagonal. So we are finally done, right? So that means that A is orthogonally diagonalizable. Okay. All right. This will not be on the test, okay? But this, maybe you can get an idea of how this would work if you had a 4x4 matrix. You would just take an eigenvector and add 3 more vectors, get a basis of R4, and then just go through all this again. And then only in this case now, then B would be a 3x3 matrix, and you just go on as before, and hopefully not make any mistakes. Right. So that proves the spectral theorem. Okay. The proof is tough, but I mean it's a very important theorem. And we're going to see some consequences of this and do another example in the next video.